This is one last truss problem here as a joint, and we're using it as a joint equilibrium problem, but we're also using it really to set you up for Chapter 6 truss analysis using the method of joints. And because you now should know enough to do that. So we apply 200 pounds. This is a truss that kind of overhangs or cantilevers out from a wall. And you got these pins at a wall. And we want to find the forces in these members. We've got this 200-pound force at D. And you say, okay, I'm going to draw a free body diagram of D, and I can find these guys. But if you do that joint at D, there's 3 unknowns in that free body diagram. And so I can only write 2 equations of equilibrium, so I'm kind of in trouble. So let's start at H. If I start at H, I've got FCH, and I have FHD. I didn't draw arrows on these guys, but I know that these forces act along these lines, either pushing or pulling, pushing or pulling. But if there's no force at H anywhere, and so no force, if I sum forces horizontally, this guy has to be 0. And if I sum forces vertically, this guy has to be 0. So these are called zero force members. And these will occasionally arise in a truss for a given loading configuration. If there's not a load at a joint, sometimes you can prove that these guys are 0. And so if you do that, these guys go away. And then at D, we're left with, this is D, 200 down. I've got FED and FCD. FCD, FDE. This is at a 3, 4, 5. This is 8, and this is 6. So this is a 3, 4, 5. Notice I didn't draw arrows on these guys yet. These are either pushing or pulling. But if you put an X coordinate system and a Y coordinate system here, and you mentally sum forces in the vertical direction, for D to be in Y equilibrium, FCD has to be pulling upward there. Once you get the direction for this guy, if you mentally sum forces in the X direction, it's clear that FDE has to push. So this guy is in tension, and this guy's in compression. This guy's pulling, this guy's pushing. Once you get this, then you can sum forces in the Y direction, and you get FCD is equal to 250 pounds. And if you sum forces in the X direction, you get FED is 150 pounds. And that's in compression. I put that tension, but that's in compression because he's pushing. Compression. Once you get these 2 members, then we can walk to D or walk to E. And so if you go to E, so we just analyzed D. And we found FED is equal to 150 pounds. He's pushing, so he's in compression. We found FCD is equal to 250 pounds. He's pulling, and so he's tension. Knowing these 2 guys, we can now walk to joint E. And if we go to joint E, it looks like this. So this is E. FCE is going to be vertical. FED is horizontal. FEF is horizontal. We just found that ED, this is FED, we found that he is 150 pounds compression. And so, which means he's pushing on E. F, this is F, E, F. And if we establish an x coordinate and a y coordinate, if we mentally sum forces vertically at E, if there's no load hanging here, then this FCE has to be 0. And so we can make him 0 if there's no load hanging at E. If we sum forces in the x direction, if he's pushing on E, then this guy has to push on E. And if he's 150, then he has to be 150 pounds, and he's compression. And so we analyzed H, we analyzed D, now we've analyzed E, and now we can keep walking our way through the truss and apply joint equilibrium joint by joint, and that's called the method of joints. It's one method for analyzing a truss. So we analyzed this truss, and we analyzed H, we analyzed D, and we analyzed E. And we could continue to walk through this truss, so we could go to C, we could go to F, and so on. And that's called the method of joints. And so when we get to trusses in chapter 6, that's exactly what we're going to do for trusses. And so you're halfway there. If you understand this, you understand part of truss analysis right now. The other method we're going to use for trusses in chapter 6 is called the method of sections. And the method of sections is where instead of taking a free body diagram of just a pin, I'm going to take a larger free body diagram and then write equilibrium equations based on that. And we basically already did that too. So when we actually looked at this overall free body diagram of this problem here, and which looked like, when I took this overall free body diagram, which is this guy, this guy, this guy, and 80. It's a larger free body diagram than just a single joint. And we applied some forces in the y direction here. This is basically a precursor, or kind of the method of sections. And so just since we've already done it, I want to illustrate it to you here. And so if we basically cut this truss here and take this right-hand piece, we draw this square, we draw this diagonal, we draw a line here, a line here, and a line here. We draw the 200 down. If I assume that this FBC is pulling here, if I assume this FFE is pushing here, and if I assume that this FCF is at a 3, 4, 5 slope, I'll draw him pushing up. And so this is my free body diagram of this piece of this truss. And so remember that we said that when we were in that multi-node problem, is I could apply equilibrium to each piece of that system. And I did that joint by joint, but now I can do that with this piece too. This piece has to be in equilibrium. Now, once you draw this free body diagram, this is no longer a concurrent force system. You've got forces acting over space, over dimensionality. And I have 1, 2, 3 unknowns. So when we get to sections, we'll basically discover that I have 3 equations that I can write here to get these 3 unknowns. I can sum forces in the x, I can sum forces in the y, I can write a moment equation, which you did in physics, and we'll do it here in chapter 4. But we don't know how to do that yet here in chapter 3. But I can sum forces in the y direction. If I do that, only one of these 3 unknowns has a y component. And so I can write 4/5 of FCF minus 200 is equal to 0. And so FCF is 5/4 of 200, which is 250 pounds. And because he's pushing, he's in compression. And so this is the method of sections. Method of sections. Which we've done twice now. We did it on these problems, and we did it here. So these 15 or so example problems have been laying a foundation. Not only are they chapter 3, but we've been laying a foundation for the rest of statics. And so, which is why we've taken the time to do that. That doesn't finish up chapter 3. So we actually have a few more example problems of 3D particle equilibrium problems that we'll do. And then we'll also work a few more problems that are called spring problems in particle equilibrium that will work. And so we're not quite done yet with chapter 3, but that's the plan. That's the roadmap where we're heading from here.